Well, good morning or good afternoon. I'm going to talk about the balance between the deposition rate and the ionized flux fraction in the HIPIMS discharge. The HIPIMS discharge gives us higher ionized flux fraction than the DC magnetron. And due to this high fraction of ionization of the sputtered species, we get overall better quality films. They are smooth, dense, we can control the microstructure, we get better mechanical, electrical, and optical properties, and better adhesion. And this has been shown experimentally. Here we see that the crystallinity is improved greatly in HIPIMS compared to DC magnetron, and this has also been demonstrated using molecular dynamic simulations. But there is a drawback. The deposition rate in HIPIMS is often significantly lower than the DC discharge operated at the same average power. And here we show the well-known curve that shows the deposition rate is significantly lower for the HIPIMS for different metals. We set out to explore the influence of the magnetic field on the deposition rate and the ionized flux fraction. So we measured the ionized flux fraction and the deposition rate with an ion meter as we varied the magnetic field by moving the magnets. And here is the deposition rate as a function of the magnetic field. For the DC magnetron sputtering case are the black circles here. We see that the deposition rate is not much influenced by the magnetic field strength. For the we look at the HIPIMS case in two different cases where we fix the voltage and vary the current to keep the power fixed, and the other cases where we fix the current and vary the voltage to keep the power the same. So if we fix the voltage and vary the current, we see that the deposition rate increases as we lower the magnetic field. And the same happens when we fix the peak current and vary the voltage. So in both cases, as we lower the magnetic field, we increase the deposition rate, and it is significantly more in the fixed voltage case. But when you look at the ionized flux fraction, we see that in the fixed voltage case, as we decrease the magnetic field, we also decrease the ionized flux fraction. But in the fixed peak current case, we increase the ionized flux fraction when we decrease the magnetic field. So these are our experimental results. So we see actually that there are opposing trends with the magnetic field strength when we fix the voltage on one hand and fix the current on the other. So we set out to understand this, and to do this, we look at the internal parameters and give a hint for optimization of the HIPIMS discharge. So the low deposition rate is actually the main drawback of the HIPIMS technology, and this hinders somewhat the use for industrial application. So the main reason for the deposition rate is believed to be the back attraction of the ions of the sputtered species. To describe this, we use two internal parameters. It is the ionization probability of the sputtered species and the back attraction probability of the sputtered species. And we can relate the measured quantities, the deposition rate, which we call here a normalized deposition rate on one hand, and the ionized flux fraction on the other hand, to these internal parameters. So we see that the deposition rate scales as 1 minus alpha times beta. So it's 1 minus multiplication of these two internal parameters scales as the deposition rate. The ionized flux fraction has a slightly more complicated relation with alpha and beta, but we have a relationship between the measured quantities and these internal parameters. That means that we can derive equations that give us the back attraction probability as a function of the deposition rate and the ionized flux fraction, as well as the ionization probability as a function of the deposition rate and the ionized flux fraction. So we can, from the measured quantities, look at these internal parameters. There are two ways of measuring how good a HIPIMS discharge is. And it is basically the deposition rate, which is the fraction of the sputtered species that reaches the diffusion region or reaches the substrate, and the fraction of ionized species in that flux. And if we plot now the deposition rate as a function of the ionization probability, we see that as the ionization probability increases, the deposition rate goes down. If we look at the ionized flux fraction, we see that the ionized flux fraction increases as the ionization probability increases. So we see that there is a conflict between the deposition rate and the ionized flux fraction. And to see what we are dealing with here for a DC magnetron, there is very low ionization of the sputtered species. The deposition rate is high. For HIPIMS, there can be a significant fraction ionized and the deposition rate is low and the ionized flux fraction is high. So this is to put this in perspective. So if we say that we need 30% ionized flux fraction and beta is high, then we get a low deposition rate. But if we can lower beta, which is moving from the dashed lines to the solid lines here, we can see that for the same ionized flux fraction, we can get significantly improvement in the deposition rate. So the key here is to lower the beta. The question is, how can we lower beta in these systems? From the measurements I showed you earlier, we can now plot the ionization probability as a function of the magnetic field. And the black here is the fixed peak current case. We see that alpha, if the current is fixed, then alpha is fixed. So alpha seems to only depend on the ionization or the peak discharge current. Even in the fixed voltage mode, where the current varies, we see that alpha varies with the magnetic field. So we see that we can basically vary alpha in the range from 0 to 1 by varying the discharge current amplitude. But we also see that in the case, the fixed peak current case, we know that alpha is fixed. So in that case, we can see that beta depends on the magnetic field. So we see that by playing with the magnetic field, we can vary beta and we can get a significant improvement in the deposition rate by varying the beta. We have also modeled this with our ionization region model. We see that the ionization probability depends on the discharge current. As we see here, it follows this rather smooth curve, but we also see that the magnetic field strength seems to control beta, or as we like to put it, 1 minus beta, because that is the measure of how much of the sputtered species ions reaches the substrate. But we see in this figure that the relationship is somewhat complicated, but we see that 1 minus beta decreases with increased magnetic field strength. We have also tried out shortening the pulse, and we see that by shortening the pulse, we can increase the ionized, the deposition rate. This is the deposition rate normalized by the DC deposition rate at the same average power. By shortening the pulse, we increase the deposition rate in the HIPIMS case, while the ionized flux fraction remains the same. And this is because beta is basically controlled by the electric field caused by the applied discharge voltage. So we see here that we can switch off the cathode potential at the end of the pulse, and that really releases the ions, so it decreases the effective back attraction. And this beta, the back attraction probability decreases with decreasing pulse length, as we see here. But we also see that alpha decreases with pulse length. So recall that the deposition rate scales as 1 minus alpha times beta, and we show by shortening the pulses, we can lower both, so we increase the deposition rate. So this is the reason why shorter pulses give higher deposition rate. We can basically optimize the HIPIMS discharge by choosing the pulse power, the pulse length, the pressure, and the magnetic field. And here we see how different parameters, operating parameters, can influence the internal parameters that I mentioned, which again influence the flux fraction and the deposition rate. So the current influences, increased current increases alpha, which increases the ionized flux fraction, but this decreases the deposition rate. So this is how we can relate this. We have also explored how the HIPIMS discharge can be optimized by mixing 2 different power levels in the pulse pattern. We can apply a HIPIMS pulse to basically create the ions of the sputtered species, and then run at the DC level to create neutrals to increase the deposition rate. So there are ways to optimize the HIPIMS discharge, and this is kind of a schema to show we can create ions by the HIPIMS pulse by choosing the parameters low beta, low pressure, short pulses, and then we can split the power between the creation of ions and creation of neutrals to optimize the process. And this we can either do empirically by choosing certain quality of the film we need, and then split the power accordingly between creating ions and creating neutrals to optimize our process. So basically, the low power pulse creates the neutral atoms, while the high power pulse creates mostly ions. So this is one approach to try to optimize the process and get the deposition rate up while maintaining a good ionized or sufficient ionized flux fraction. To summarize what I have said, we have shown that the magnetic field strength has a significant influence on the deposition rate and the ionized flux fraction. But there is a conflict between the goals of high deposition rate and high ionized flux fraction. And we have demonstrated that the HIPIMS discharge can be optimized by adjusting the pulse power, pulse length, and the working gas pressure, as well as the magnetic field strength. So we basically have to start by deciding how good of a film we need, what is the density, and what are the properties we need. We can then choose the ionized flux fraction we need, and then optimize the discharge with regard to the deposition rate. So this is the message. Thank you for your attention. Note that you can download the talk at the link shown here.